Hey guys, welcome to the Biomechanics 1 video series. Just thought I'd put a quick video together that takes you through the review answers of your actual test. So seeing that the test should be relatively fresh in your mind, by me going through most of the calculations in a little bit more detail, it might help you understand better where you might have gone wrong or how you got to the correct answers in instances where you may have guessed, especially in this multiple choice section. So the first question asks you, instantaneous acceleration at a given event can be obtained from, and you have 5 possible options. Well, by definition, acceleration is a vector quantity that is equal to the change in velocity over the change in time. Remember in class when we went through a velocity versus time graph, right, that may have looked something like this, and we took the slope of a velocity versus time graph. This would be the change in v, and this would be the change in t. So the slope of a velocity versus time graph is equal to the change in the velocity over the change in the time, which is equal to the acceleration, right? So in your different options that you have here, you will see that C is the correct choice. The acceleration versus time graph as the slope of the line tangent to the curve at a given point would be the correct answer. Alright, what about number 2? Calculate the average velocity when something is displaced from x equals 8 to x equals 9 in 6 seconds. So in essence, pretend you have a number line, pretend that that's pretty straight, and we have some point along the number line where x is equal to 8, and then you move to some point where x is equal to 9, right? This could denote meters, centimeters, some other length, right? And you cover this distance in a period of 6 seconds, right? So the average velocity by definition is equal to this change in the displacement over the change in time, right? Well, change in displacement is just the final minus the initial over the change in time. Well, in this case the final was 9, that's where I ended up. The initial where I started from was 8, and the change in time was 6, so this should be equal to 1/6 of a second, meters per second, right? Meters per second, since we're dealing with the average velocity, so that should give you B. In terms of question 3, if an object is displaced from x equals 1 to x equals 19 and then displaced back to x equals 10, determine the displacement and the distance traveled, right? Oops. So again, if I had a number line here, let me try and draw that a little bit straighter. So if I had a number line here, it looks something like that. I started at x equals 1. I traveled some distance to x is 19, right? So I went all this way, and then from 19 I went back to x is equal to 10, right? So I went back this way. So the displacement, which we'll just call x, is the shortest distance, right, from my starting point to my ending point, right? So since I started over here, that's my start, and I ended over here, then this would be my displacement over here, right? So if I ended at 10 and I started at 9, then that displacement is at 1, then the displacement is equal to 9. Okay, if I'm looking for the total distance covered, well, I went from 1 to 19, so that total distance is equal to 18, and since we're dealing with centimeters here, and then I went and covered an extra 9 on top of that, so the total distance would be plus an extra 9 centimeters, which gives me a total of 27 centimeters. Okay, so remember, distance does not take into consideration direction, right? It just gives me the total magnitude of how much I covered, right? Displacement does take the direction into consideration. So if I started here and I ended here, I had a net displacement of 9 centimeters to the right. So right is by convention typically given a positive value, left a negative value, but the distance does not take direction into consideration, right? So you wouldn't subtract any of this from each other, so on and so forth. So it's just looking at the total. So my answer then should be 9 and 27, which is option number B. Okay, question number 4. An object is displaced from position x equals 7 to position x equals 17 in 5 seconds. It's then displaced back to x equals 10 in 20 seconds. So probably the easiest thing to do here to keep track of everything is kind of just draw yourself a graph of sorts. Right, so we started off, we can use a position versus time graph to denote the answer. We started off at 7 and ended up at 17 in 5 seconds, right? So you can kind of draw a graph like that, and that's the 5-second mark. I then went to the 10-meter point in 20 seconds. So from here, I went back to the 10-meter point in 20 seconds. So let's say this was 20 seconds over here. So 17, then I went down to 16 and 15 and 14, 13, 12, 11, 10. Okay. So if the question asks for the average velocity, remember it's just my starting point and my end point connected, right? So let's see if I can just draw that straight line. That's kind of good enough. There we go. Right. So average velocity is just concerned with this change in the displacement over the change in time. Right. Well, if I started at 7 and I ended at this 10 over here, so 10 is my final, 7 was my initial, and the change in time, well, that took a total. This shouldn't actually be 20, this should be 25, right? Because it took me 5 seconds to get to here, and then this over here, this total, the difference between this and that is 20 seconds, so that should be 25. So my total time of my trip is 25 seconds. So this should be 3 over 25, which should equal 0.12 meters per second. Okay, average distance, or average speed, sorry, is the total distance covered, right, over the total time. Well, the total distance is, I went from 7 to 17, so that's 10, and then from 17 back to 10, that's another 7, and the total time was 25. So I have 17 over 25, which is equal to 0.68, and that's also in meters per second. So you'll see that C should be my correct answer. Okay, question number 5, almost halfway there in terms of my multiple choice questions. This was the same one, so this was a typo. So this is the same as question 4. So the answer should be C. So sorry about that one. Question number 6. An object starting from a certain speed was accelerated for 10 seconds to a speed of 18 with constant acceleration. Okay, so this constant acceleration should give you a clue that we're using the equations of uniformly accelerated motion. Remember, you have 3 equations. They're given at the back of your question paper. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times displacement. The final velocity is equal to the initial velocity plus the acceleration times time, and the displacement, or the change in displacement, is equal to the initial velocity times time plus 1/2 acceleration times time squared. Okay, so I normally just write these down, then I look at what are the values that I have. So starting from a certain speed, which means the initial velocity is probably what I'm looking for. The final velocity was given, it's 18 meters per second. It was accelerated for 10 seconds, so the time through which this tends to act is 10 seconds. And the constant acceleration is equal to 0.6 meters per second squared. Okay, so I have 3 knowns and 1 unknown. So you'd see that this is probably, the second equation is the one that's probably easiest to use. So if I just rearrange that, if I say Vf is equal to Vi plus At, I'm trying to solve for Vi. So Vi is equal to Vf minus At. Then I can just plug in the values that I have. It's 18 minus the acceleration, which is 0.6, and the time is 10 seconds. So I should have a value of 12. Let me just double check on my calculations. Yep, it definitely is 12. So it's 12 meters per second, and that's E over here. Okay, and object is moving with an initial speed of 8. So again, still using my constant acceleration formulas because it is uniformly accelerated. So my initial velocity is 8 meters per second. It was accelerated uniformly for 8 seconds, so the time is equal to 0.8 seconds. Calculate the speed after it's traveled, so the distance that it's traveled is 80 meters, right? So it's asking for the final velocity. I have 3 knowns and 1 unknown, but I only have these 3 equations over here. So if I look at the first one, Vf is what I'm looking for. I have Vi, I don't have A, but I have S. So I have 2 unknowns and 2 knowns. Can't use that one. Vf is what I'm looking for, don't have it. Vi I do have, again acceleration I don't have, but time I do have, can't use that one. I have the distance, I have the initial velocity, and I have the time, but I don't have acceleration. Okay, so what I would need to do is utilize this third equation to solve for the acceleration. Once I have acceleration, I can plug it into one of these 2 other formulas to solve for the final velocity. So if I take this one and I just rearrange the formula slightly to make acceleration the subject of the formula, you would find that, let me just rewrite it out and show you step by step. So this change in displacement is equal to Vit plus 1/2 At squared. So the first thing I do is get this Vi to the other side. So it's this change in displacement minus the initial velocity times time is equal to 1/2 At squared. To get rid of this half, I'll multiply both sides by 2, so then this becomes 2 change in S times Vit is equal to AT squared. Let's get this down a little bit here. Now I have to get A by itself, so I just divide both sides by this T squared, so this becomes 2 S over VIT over T squared is equal to the acceleration. So I'm just going to calculate all of that over here. Well, now I can plug in the values, right? So it's 2 times, sorry, let me just undo that, 2 times, the change in distance was 80 minus the initial velocity was 8 times the time, which was 0.8, and all of that over 0.8 squared, which gives me an acceleration of let me just double check, 230 meters per second squared. 230 meters per second squared. Okay, now I can chuck it into, let's just use the simplest one, which is the formula which says VF is equal to VI plus AT. So my initial velocity was 8 plus 230 times 0.8, and that should give me a 192 meters per second, which is A. Okay, number 8. Speed is still uniformly accelerated, so we got quite a few uniformly accelerated motion equations. Changed from 800 meters per second to 100 meters per second, so my final velocity is equal to 800 meters per second. My whoops, that's not final, it's my initial velocity was 800, that's what I started off with, meters per second. It then went to a final velocity of 100 meters per second in a distance of 250 meters. So again, this S is 250 meters. So calculate the acceleration as well as the time taken respectively. Okay, this one should be pretty straightforward. Vf squared is equal to Vi squared plus 2As. Well, I'm trying to solve for acceleration, and I've got these 3 other values, so I'll just rearrange this and say acceleration is equal to Vf squared minus Vi squared over 2 times S. Plug in the values. Vf is 100 squared minus 800 squared over 2 times 250, and you'll find that the acceleration here works out to be something along the lines of negative 1260 meters per second squared. I can then plug this into another equation to solve for time. The easiest one to use is just this: Vf is equal to Vi plus At. Since I have acceleration now, and I have Vi and I have Vf, I can solve for t. So t is equal to Vf minus Vi over A. So that's 100 minus 800, which will give me a negative number, over negative 1260, and I should have a positive time of 0.556 seconds. Alright, so my acceleration is negative 1260, time is 0.556, so let's see if I can see that here. There we go. Option number B. Solved. 2 more left. Okay, which of the following explains Newton's second law? So let's just write Newton's second law down. So Newton's second law states that the sum of all forces is equal to the mass times the acceleration, right? So in other words, the sum of forces acting on an object is going to be proportional to the acceleration acting on that, or the acceleration that the object tends to experience. Therefore, if F increases, A will increase by the same amount, right? If F doubles, A doubles. So this should be answer number A. Right? When a force acting on an object is doubled, the acceleration is doubled. B, when a man fires a gun, an object looks backwards. That's just Newton's third law, right? Action-reaction. Man walking forwards while pushing on the ground is backwards. Newton's third law. Again, action-reaction. When a driver applies brakes suddenly and the body jerks forward, that's Newton's first law. Right, law of inertia, and an object falling in a straight line with constant speed. Newton's first law. That's it, law of inertia again. Alright, so that was number A. Let's look at number 10. Under the influence of a certain force, the velocity of a 10 kilogram object increases from 16 meters per second to 50 meters per second in 80 seconds. Calculate that force. Alright, so while we're given the mass of an object, there's a change in velocity, so we can probably calculate the acceleration when we have the time. Alright, so the acceleration that an object experiences is equal to the change in velocity of a change in time. Well, change in velocity is just the final velocity, which in this case was 50. Initial velocity was 16, and the change in time was 80, which gives me an acceleration of 0.425 meters per second squared. Okay, well, since the force is equal to the mass times the acceleration, all I have to do is multiply the acceleration by the mass to get the force. Mass was 10 kilograms, 0.425 was the acceleration, which gives me a final force of 4.25 newtons. Option number A. Awesome. Okay. So that should give you an overview on how to solve the multiple choice questions. Some of them a little bit trickier than others, but all solvable and all utilizing equations that you guys have already learned in class. Some definition terms. So this is all theory and very, very brief. Let me just give a quick overview. Right. Force, basically tendency to push or pull, right? Therefore cause change in motion, right? And a change in motion implies that there is some kind of change in velocity that tends to happen, right? Something could have been at rest, or it could be moving at constant velocity, or the velocity can be changing, right? So that's in essence what the definition of a force entails. Inertia tends to refer to a body's resistance to change motion, and it's also proportional to the mass of that object, right? So whether something is at rest, it'll want to stay at rest, or when it's moving, it'll want to stay moving, and it therefore resists changes in motion. That's known as its inertia. Mass is the total quantity of matter / atoms that composes a body. Weight is basically just the gravitational acceleration of mass. Gravitational acceleration of mass. I'm just going to put that battery in quickly, just so that this whole thing doesn't die on me. So just give me a second, please excuse the background noise. Just need to make sure that this whole video still works at the end of the day. That's better. Okay, and then when we look at projectile motion, projectiles is defined as an unsupported body that is basically just subjected to gravity and air resistance. Okay, brief overview. General motion. General motion consists of translation and rotation, right? So your job basically is to define both of these aspects. So translation can be curvilinear, or rectilinear. So again, you want to unpack that, and then this rotation is motion around a fixed or imaginary axis. Right, and then you can unpack that a little bit more, but in essence that's what that entails. Primary factors that govern projectile motion. So there's 4 to 5 factors. One is velocity of release. Second is angle of release. Third is height of release, and how does that impact the previous two? And the fourth one was landing height, right? You could have added a fifth one, which was the air resistance, if you wanted to. But in all of these, we want to unpack how the angle changes when the height of release changes, or in the landing height changes. And out of all of these, the most important one was your release velocity, right? In terms of range, there's a link between range and velocity squared, so it's the most important factor. It tends to have the biggest impact in terms of maximizing the range of an object. 8. So you have a runner that has an approach speed of 20, and he asks you that when he lands, what will his approach speed be? You know, does he slow down? Does he speed up? Is it going to be the same? What's the deal? So you requested to explain your answer in detail and include the relevant laws of motion. So which of Newton's laws tends to apply in the situation? Okay, so we have a case where you have projectile motion, right? And you're told to ignore air resistance. So when this projectile is in the air, which is the definition of a projectile, there's only typically 2 forces acting on it. One is the force of gravity, and 2 would be air resistance, right? So if the jumper was going through the air in this direction, air resistance would be impeding his motion, but we're told to ignore that. So the only other force is gravity. So Newton's first law, right, the law of inertia, says that a body will continue in its state of motion unless some external unbalanced force is acting on it. So the only external forces acting on us are gravity, right? And there's no air resistance. So therefore, gravity only tends to act vertically, so it would obviously affect his vertical motion. It's one of the reasons why he tends to come back down to earth, right? Doesn't continue into space. But horizontally, there's no other forces. So horizontally, his motion is unimpeded. There are no external unbalanced forces. Therefore, velocity on landing, or the final velocity, is equal to the initial velocity. Okay, so if he left with 20 meters per second or 20 kilometers per hour, his velocity, horizontal velocity on landing, should also be 20 kilometers per hour. Okay, so you can unpack it under the definition of Newton's first law. Okay, so question 9 and 10, it's just some more calculation based ones, should hopefully not have been too hard. It's based on the Olympics of 2016, where Kenya's Vivian Cheruiyot broke the women's 5,000 meter record in a time of 14 minutes and 26 seconds. average speed for the entire race in meters per second, meters per minute, and kilometers per hour. So remember that average speed, right, is a function, or the units of speed is always some length over some time, right? Where length can be in meters, can be kilometers, can be in centimeters, some other length over some times, which can be in seconds, minutes, or hours. Alright, so whatever units we need to put in here are going to be dependent on what our answer requires, right? So in meters per second, I am required to, so let's make this 9.1.1 meters per second is the requirement. So it means the top value must be in meters, the bottom value must be in seconds. So 5,000 meters, that's already, I don't need to convert that, that's already in meters, divided by seconds. So I have to convert 14 minutes and 26 seconds into seconds. So 14 minutes is how many seconds? I just do 14 times 60, right? That'll give me the 14 minutes, but then I must add 26 seconds to that. So in essence, this is going to be 5,000 divided by 866, which gives me a value of 5.77 meters per second. 5.77 meters per second. Okay. 9.1.2 meters per minute. Same convention, right? Top values in meters, so I leave that unchanged. Minutes, ooh, okay. Well, I've been given it in 14 minutes, but this 26 seconds tends to throw people off. So people will tend to write 14 minutes and 26 seconds as a decimal value of 14.26. This is not, however, true. You have to take this 26 and divide it by 60 in order to get the decimal places, which then means that this becomes 14.433, right, minutes. So I should have divided this by 14.433, and I get a value of 346.42. 346.42 meters per minute. And then the last one, 9.1.3, is kilometers per hour. Okay, so 5,000 meters is 5 kilometers, and 14.433 minutes is how many hours? So I take 14.433 and I divide it by 60 to get hours, and I'm left with 20.79 kilometers per hour, pretty close to 21 kilometers per hour. That's how quickly she was running that 5k time in. Okay, so that's 9.1 sorted. Alright, 9.2, calculate her average lap time. Okay, this one's also relatively straightforward. So she ran, and give your answers in seconds. So she ran 5,000 meters in 14 minutes and 26 seconds. We've already converted this to seconds, right? We said that this was 866 seconds. Okay, so we're almost halfway there for this question. Average lap time. Okay, so in essence, she's running around a 400 meter track. And we're saying how many times does she have to run this 400 meters? How many times does she have to run around this 400 meter track in order to equal 5,000 meters? So to find that out, you can say, well, you can do it manually and say 400 plus 400 plus 400 plus 400 and add it all up. But in essence, it's saying that I have to multiply something by 400 in order to get this 5,000 meters, right? How many times does she have to run 400 meters in order to equal 5,000? Well, you can solve that then and say x is equal to 5,000 divided by 400. and you'll get that it's 12.5. So she has to run 400 meters 12.5 times to equal 5,000 meters. So we can say that another way of saying the same thing, 5,000 meters in 866 seconds, you can say that she's basically running 12.5 laps in 866 seconds, right? So if I want to say 1 lap, I can divide both sides. If I just write this a little bit more mathematically, say 12.5 is equal to 866 seconds. So to divide this by 12.5, I have to divide this by 12.5 in order to get 1 lap. So 1 lap is equal to 866 divided by 12.5, which is equal to, it should be like 69 point something. You'll get a decimal point here too. It is 69.28. 69.28 seconds, or just over a minute, right? So she kept an average pacing of about 69 seconds per lap in order to complete the race in that time. Okay. Last section, so question number 10. Gold medal men's discus. Let me just tick that off, we've done that one. Was won by German Christoph Harting. His release velocity was 133 meters per second at an angle of 20 degrees horizontal, having released the discus 2 meters above the ground. So you could draw this out and you'll get a rough indication of what's going on here. So you have this German guy throwing a discus, right? So here's his ball. This height here is 2 meters above the ground, right? And it's going to fly through the air and ultimately land somewhere, right? It gives us, I didn't put that in, okay, it doesn't matter. I think he broke the record in just over like 68 meters, right? So from where he released it to where it ultimately lands was about 68 meters. Not so interested in that right now. The goal here was to say, okay, well, he released it at some angle, right, to the horizontal with some speed. We said, okay, it's 33 meters per second, and the angle was 20 degrees, and it was 2 meters above the ground. So what was the total time in the air, the height above the ground that the discus reaches at its peak, and the range of the discus? Okay, so I've really kind of given you the answer for this, so you should get something relatively close to this. So let's start with 10.1. So 10.1 says time in air, but now we have a scenario whereby your release height is greater than your landing height. So there's only one time formula that you can use. I'm going to write it out. It's in the formula sheet. It looks something like this: v sine theta plus the square root of v sine theta squared plus 2gh and all of that over g. The first thing that you guys would have to do is, if you look at this release velocity, is convert it into its or decompose it into its horizontal and vertical components. So the vertical component is just 33 times the sine of 20, right, which is equal to, if I just do it on the calculator quickly, 33 times the sine of 20 is 11.29. That's 11.29 meters per second. The horizontal component is 33 cosine of 20, which is something really small. So 33 cosine of 20, it's 31, approximately 31 meters per second. 31 meters per second. Okay, so I'll only need this vertical component, because if I rewrite this, it's just the initial velocity times the sine of the angle, right? So notice that that's the value that I technically chuck into this equation. So this will just be 11.29 plus the square root of 11.29 squared, plus 2 times gravity is just 9.81, and the height is 2 meters, right? And divide all of that by gravity, which is 9.81, and I should get a time value, right? So you'll find out how much time this particular object spent in the air. So if I just had to do it on the calculator for a second, 11.29 squared, right, plus 2 times 9.81 times 2, square root all of that, don't forget to square root it, is equal to 12.91. So if I just chuck that in here, so this would be 11.29 plus 12.91, and all of that over 9.81 divided by 9.81 gives me 2.47 seconds. 2.47 seconds. That's the total flight time of the projectile in the air. The height above the ground that the discus reaches at its peak. Remember, this one now, if I look at 10.2, if I just redraw the scenario, so part of your calculation will give you this value, right? But you are asked what is the height above the ground. So remember, all of this was 2 meters, so that's something I have to add in. So my next step is to calculate this first. So remember, here at the top I have my final velocity being 0 meters per second. I have some release velocity, but when I do all of this, remember, I'm just looking at the vertical component, and I have acceleration in the y direction being 9.81 and negative value. So one of your uniform accelerated motion equations that you have is this Vf squared is equal to Vi squared plus 2as, right? I have acceleration, I have initial velocity, and I have final velocity. Remember, all of these values are in the y direction because I'm trying to solve for height, which is a vertical component, right? So final velocity in the y direction, let me just rearrange this so that I make s the subject of the formula. So sy is equal to vfy squared minus vi y squared over 2 times ay. Well, vf is just 0, because that's what we said here at the top. So this becomes negative viy squared over ay is just gravity. So this becomes negative 2 times g. So now I can just plug in values, right? We said that this is 11.29 squared over 2 times 9.81, and that gives me 11.29 squared divided by 2 times 9.81, 6.49 meters or 6.5 meters, you can round it off, 6.5 meters. So that tells me what this height here is, but I have to add this 2. So total S is 2 plus this 6.5, giving me a total height of 8.5 meters above the ground. Alright, then the last question, 10.3, saying calculate the range of the discus, how far it was thrown. Okay, so very last one, and just find out, there we go. 10.3 asks for range. Remember that we could find out the range, which is the displacement in the x direction, by utilizing this formula: velocity, initial velocity in the x direction times time, plus 1/2 acceleration in the x direction times time squared. But if we ignore air resistance, and acceleration in the x direction is just equal to 0 meters per second squared, and 0 times anything is 0, so that just falls to 0. So I'm just left with this component. So it's saying that the range in the x direction is Vix. Vix is the initial velocity in the x direction, right? So from what we've calculated here, so what is the component of this acting horizontally? And we said that that was equal to this over here, so it's 31 meters per second. So if I take this 31 and I multiply it by this 2 point, what did I calculate for this time? 2.47, I should get my range, which is equal to 2.47 multiplied by 31 is 76.57. 76.57 meters. You'll remember earlier that I said the actual world record is this 68 over here, and you know we're sitting with a value of 76, but remember the 76 does not factor in air resistance, right? So what you actually find is you factor in air resistance into this equation, you would get an answer that is pretty darn close to that 68, which is the actual world record. This is how much he would have gotten if we completely ignore air resistance, but that's beyond the scope of what this test was asking you guys. Alright, so lots and lots of information, but again, not overly complicated, and it's all information that you guys have had exposure to. So I hope that's made some sense, and if you guys don't understand anything, please come and see me. Thank you.